Alright, so we are in AP Calculus BC. We are in worksheet 2-4. Our instructions say we need to find the dy dx derivative of the following parametric functions. And again, these should all be in terms of x for our final answer. So this one looks very similar. So we could totally convert this to Cartesian if we wanted to. I'm going to be using the formula because kind of the one true like hammer method. I'll just keep using that hammer on every single one of them. Here we go. Again, our formula, I'll write it once and then I won't write it again from here. Our dy dx. The definition is I first do the dy dt and then I divide that thing by dx dt. And hopefully you'll remember it's always the y over the x. From there, what do we do? Okay, so dy dt, the derivative of that thing is 4t to the power of 3. The derivative of 2t squared is, and then plus 3, that's a constant so it goes away, is 4t. 4t. And then I need to simplify a little bit. I see a 4 and a 4, so those cancel each other out. Maybe I need to use a different color. Those cancel each other out, and 3 minus 1, there's an invisible 1 right there, is 2, so this is t squared. I'm not done because it's not in terms of x. I need to get it in terms of x, so I need to somehow get a t squared isolated because that is t squared. So I'm going to isolate for that t squared, and I get, let's come over here. This is going to be x minus 3, and then divide by 2 is going to be equal to my t squared. And I'm going to use that to put right there. So my final answer is as follows. dy dx is equal to, those are a direct substitution. There's no extra work that I have to do. So it's just x minus 3 divided by 2. And box it. So the squares and square, they're the same exact term, so it's a direct substitution. I could square root both sides and then undo the square root if I wanted, but I think this is a faster method. Question, Fiona? Oh, okay. I'm going to leave that frozen up on the board while I take a look at number 2. Oh, yeah. All right. All right. So I'm going to move on to number 2 then. I'll zoom out so people can still see number 1-ish. Number 2, I'm going to use the same formula. I'm going to take the derivative of y, and that's going to be 4t to the power of 3 minus 6t squared. And I'm going to divide that by the derivative of x, again with respect to t, and that's going to be 2t. All right, so now I'm going to try to cancel things out a little bit, simplify. So the greatest common factor on the top is 2t squared. And what's left over when I factor out the 2t squared is a 2t minus 3. On the bottom, I still have that 2t. Oh, the 2's and 2's cancel each other out. So whenever things are being multiplied, that means I am allowed to start canceling them out. If you see, I can start crossing them out now. You can if you're careful. If I'm not careful, then I'm going to factor them out like this. This is kind of like the long way of doing our problem. So the 2 and 2 cancel each other out. The square and the t cancel each other out. And then I'm left with t times the quantity of 2t minus 3. And from there, I can simplify that a little bit, and that's 2t squared minus 3t. Okay, so there's the derivative, but I need it in terms of x, and that looks like it's going to be a challenge because I have this t squared minus 1. So I can find what t squared is, and I can find what t is. Okay, so I'm going to have to find both what t squared and t is because I have a t squared and I have a t. So how am I going to do this? Let's start it. I really have x plus 1 is equal to t squared. So I solve for t squared. If I want to solve for t, well, I take the square root, and t is equal to the square root of x plus 1. So I have t squared, I have t squared. I'm making those substitutions now. So this is t squared, this is t squared, this t squared is x plus 1. So I come back down here and I say this is now equal to, I'm going to do a little wavy line, this is now equal to 2t squared, and t squared is x plus 1. Then I say minus 3t, and what is t? T is the square root of x minus 1. So this is times negative 3 square root of x minus 1. And I could simplify that just a little bit, and I could say, yeah, that's equal to 2x plus 2 minus 3 square root of x minus 1. It is x plus 1, yeah, good catch. Log it.
Give it to someone else.
That has not been established yet. All right, and let me check the time again. We get out of here at 52. We still got 3.5 minutes. All right, I'm doing problem number 3 now. Ooh, we have some cosines and sines. I wonder if we're gonna have to use any trig identity functions. So again, I start with the dy dt, or dy d theta in this case, because it's not with respect to t. So if I take the derivative of y, I get 3 sine squared of theta. And I'm hoping someone is confused right now and is going to ask that question. I'll ask it. Where did that come from? Where are the 3? Well, this y equals sine to the power 3 of theta is really the same thing as sine of theta quantity to the power of 3. It's just another way of writing it. So that 3 came down in front. That's where the 3 came from. Then it goes down to the power of 2, but then the 2 comes back on the inside. So that was the derivative of y with respect to theta. And I'm going to do the derivative of x with respect to theta. And what is that going to be? So I'm going to say that's all over 3 cosine squared of theta. Okay, so obviously if I'm simplifying this, the 3's and 3's cancel each other out, and I'm left with just the sine squared over the cosine squared.
Is there a negative by the cosine? No.
I totally forgot that. Dang it. Thank you for making me learn, Arrow. Thank you for catching extra credit. Totally was a -3, yeah, because cosine. Good catch. And I'm thinking, I totally messed up on the other derivatives. Okay, there's a giant other mistake here. If anyone wants to find it. More extra credit. Where is it?
Cosine squared. I'll take it, don't worry.
So it's related to what Arrow said. I'm going to undo that because that's going too many layers in depth. I did not take the derivatives correctly. Who can take the derivative correctly?
You forgot the negative.
Well, that's part of it that she said. So if I'm taking the derivative of the outer, what is the outer house? The power of 3. What's the inner house? Did I ever do dinner? What is dinner? If someone tells me dinner, I'll give you the extra credit point.
1.
No.
It's cosine.
Yeah, so the derivative of sine is cosine. So this needs to be multiplied by cosine of theta. I don't know. Whoever wants it, log it. If you think that you felt that you deserve that point, you can log it, and I'm not going to argue against you. And then the derivative of the inner of cosine is negative sine. Negative sine of theta. Perfect. So there it is. There's the correct derivative now. And again, the 3's and 3's do cancel each other out. I'm trying to think, is there going to be a nice way of canceling these guys out without using too many trig identities? This is not a good problem. So give me a sec. So now that we have dinner correct, we can start canceling things out. So again, remember that the sine squared means there's 2 of the sines on the top. So when I'm canceling out, I have 1 sine on the bottom, 1 sine on the top. Chunk. So I still have 1 sine on the top after I cross those out. And same thing for the bottom. 1 of the cosines on the bottom, 1 of the cosines on the top. So when I simplify this thing, it looks like this. I have don't know what's going on there with lag. I have a sine of theta on the top, and on the bottom I have a negative cosine of theta. All right, and that's about as far as you can get it, but there's something that's kind of cool in terms of simplifying that even further. I can think of this as tangent, and you might be saying, how do you know that sine divided by cosine is tangent? Well, think about this. Sine is equal to opposite over hypotenuse. That's a bad H. Let me zoom in so it looks neater. Opposite over hypotenuse. Remember, so, and then this is going to be ka, and then we'll eventually get toa. So ka is A over H. And if you keep it, change it, flip it, this really looks like this. I have opposite over hypotenuse. Change it, instead of division, it's now multiplication. So change it and then flip it. H over A, and then the H's cancel off. H is gone, and I have O over A. This is equal to O over A. And what fraction is that? It's O over A, it's TOA, so tangent. So that's equal to tangent of theta. So, and I guess I forgot about the negative too. So negative tangent of theta. And that's as far as I can get. There's not a way that I know of to get rid of the theta and turn it back into an x. There might be some cool trick with cosine cubed that I don't know, but that's as far as I'm going to be able to go. And I realize that this kind of not consistent with the rest of our homework problems, but sorry, there it is. And I think probably some future problems are going to be like that too. Let's try number 4. So again, derivative of the y on the top. So derivative of y is 1, and then I'm going to do, I know it's minus, but I'm going to really show you the long step. So e house, the daughter of e house is e to the negative t. It's still the same thing. And then I multiply by the derivative of whatever the inner is. So the derivative of that negative t is negative 1. So it's really negative e to the negative t. And that's all going to be divided by the derivative of x. Well, the derivative of 1 is nothing. It's a constant. The derivative of e house is e house. So I'm going to rewrite this negative e to the negative t. And then I'm going to multiply that by the derivative of this inner, or negative 1. Simplifying this a little bit, I have 1 minus e to the negative t, all of that divided by e to the negative t. And you might be thinking, oh, well, you have something on the top, something on the bottom, cross them off. No, you are wrong. That's not how that works, because you can't cross things off when they're being added or subtracted. You can only cross them off when they're being multiplied. I'm trying to think of a way that I could simplify this even further, and I'm not seeing an answer. Let me play around with this a little bit. I might cut this out later, but this is kind of how I'm thinking about the problem. So I'm thinking this is really saying 1 minus 1 over e to the power of t. That's the numerator, right? And then this is all divided by, I can bring this e to the negative t up to the numerator also. So I can make this, all of this times the quantity of e to the power of t. And now I don't have any negative powers, and this actually makes it kind of nice. So if I multiply these together, what's going to happen here? So I'm distributing this e to the power of t into both of these two terms, and when I do that, I have, well, e to the power of t times 1 is e to the power of t, and then e to the power of t times this fraction is e to the power of t divided by e to the power of t. They're everywhere. And then, hey, that guy's 1. So that simplifies, there's cancel out, and that's just 1. So our final answer is e to the power of t minus 1. And that's as far as I can go, unless, is that solvable for e to the power of t? Not really. I mean, again, I'll play with it. So I'm definitely keeping that part in, because that's as far as I think I can go. But let's see if I push the limits on what I think I can do. And this is kind of how math works. You just play with it, see if it works. So I want to try to see if I can isolate an e to the power of positive t, and that's going to be a little bit difficult. If I can do that, then I can substitute that in so I get an x here. Let's try it out. So I start with this. I'm going to do like a little wavy line saying, hey, I'm going to try doing some scratch work. X is equal to 1 minus e to the negative t. 1 minus, just write it down, e to the negative t. That's our x. So really what I have here, I'm going to switch these two functions by adding e to the negative t to both sides and subtracting x from both sides. So I have 1 minus x is equal to positive e to the negative t. So I'm getting it more isolated, but now it still has that negative power. So what I can do is I can, think about like flipping it, I guess. When you flip it, you have to be careful that you're not going to have any domain problems, but I don't think, as long as x is not 1, we should be okay, because what I'm about to do is I'm going to say, I'm flipping both sides, and I'm saying that this is now 1 over 1 minus x, but that's a problem if x is 1. Now I'm dividing by 0. I'm using the curse word, and there's nothing in this problem that said x, or that t is not equal to, or that x is not equal to 1. So we're assuming now that x can't be 1, otherwise we're saying a swear word, and then that's equal to e to the positive t. And this is a complex way of saying what I'm really doing here. I'll do it off to the side and erase it. I really have 1 over 1 minus x. Well, too long. Let's do it like this. I'm really saying 1 minus x is equal to 1 over e to the negative t, and then I say that's over 1, and then I flip the top and bottom, so it's 1 over x. I flip the top and the bottom to make this a positive t and get the positive t there. And that's where all of that math is coming from. And then from there, I have e to the power of t, and it's equal to 1 over 1 minus x. So I come back up here and say, hey, you, e to the power of t, I know who you are. You're 1 over 1 minus x. So I can come back here and say, this is now equal to 1 over 1 minus x minus 1. Again, that minus 1 is just kind of copied down. And that is as far as I can go. I didn't even realize I could go that far. I assumed that I was going to have to stop right here because that's what the answer key from the student that made this homework assignment. So cool. We could push this even further if we wanted to and making it a different form. And I hear you yelling, "Stop, Mr. Snell, you've gone too far." And I'll stop right now. At least it's written in terms of x, and that's kind of what I'm after. I'm kind of sad that 3 is the only question that we haven't been able to do that. I'm sure we'll hit another one where it's kind of impossible. Again, I'm taking the derivative of y. Derivative constant is nothing. Derivative of a natural log is 1 over whatever was on right there. So I have the derivative of y is negative, because it's still negative. 1 divided by 1 minus t. That's the doubter. The derivative of the outer, the derivative of natural log. But then I have to do the derivative of the inner. And you might think it's 1, but you're wrong. It's negative 1 if you thought that. So this is going to be times negative 1. So that's the numerator, and then the denominator is the derivative of this thing. And I can't take the derivative of a fraction unless I use quotient rule. So I need to rewrite this. So I can say x, you are really 1 minus t, all of that to the negative 1. Okay, now I can take the derivative of that. So first I have powerhouse, so this negative 1 is going to come down in front. I'm going to say this is negative 1 times 1 minus t, all of this to the power, it goes down to negative 2. That was the derivative of the outer house, the powerhouse. And now I'm going to take the derivative of the inner house, and you might be thinking 1 again, but again, it should be negative 1. So times negative 1. We have a bunch of negatives happening here. So let's simplify this complex thing. What's going on? In the numerator, I have a negative times a negative is a positive. So I have a positive 1 over 1 minus t. In the denominator, I have these negative ones also kind of cancel each other out. And I just have 1. I'm going to get rid of this negative 2 and bring it to the denominator. So 1 over 1 minus t quantity squared. So I have nested fractions. Whenever you have nested fractions, you keep it, change it, flip it, right? So I have plenty of room. I'm going to go down to the next line. Keep it, 1 over 1 minus t. I'm just copying down this fraction right here. I'm going to change this division symbol. It used to be a division symbol like that. I'm going to change that to a multiplication symbol, and then I'm going to flip this. So it's 1 minus t quantity squared, all divided by 1. And this problem actually looks pretty nice now that we've got to this step, because now I can cancel out 1 minus t on the bottom, cancel out one of the 1 minus t's on the top, and I get 1 minus t. So that's good, but I want to solve for x. I want to say, what is this thing in terms of x? So I need to somehow isolate 1 over 1 minus t, which is really close to this thing. So all I have to do is take the reciprocal, and then I'm good. So I'm going to play with this guy. We're rewriting it. We're doing scratch work. Eventually, I'm going to come up here and say, oh, yeah, look at the answer. The answer is blah, whatever. But I have to do the substitution. That was an interesting noise, wasn't it? So rewriting, this is still x is equal to 1 over 1 minus t. I'm playing with this guy. And I just want to flip both sides. So this is technically, let me switch the colors here so it pops a little bit better. This is really x divided by 1. So I'm going to flip both of the left side and the right side, which you're allowed to do as long as you don't have any domain errors. So again, by doing this, now I have to assume that x is not 1, or x is not 0, because otherwise now I'm divided by 0. Again, a curse word. That's not okay. And I get 1 over x, because I flip that side, and is equal to 1 minus t. Technically divide by 1, but I'm going to ignore that. So just 1 minus t. And 1 minus t. That's what I have, 1 minus t. So that 1 minus t is 1 over x, and the answer here is 1 over x. Yeah, pretty cool. And I'm thinking, I know it has a derivative of 1 over x. What must really be happening here is this is kind of like the natural log of a function, probably plus or minus some constant, represented in this, man, I'm forgetting the name of this parametric equation, and somehow we got 1 over x. Anyway, kind of cool that we got 1 over x. Let's move on to our final problem, number 6. And ooh, this guy looks like it has product rule. Oh boy. So product rule, I have a function times a function, so it's 1d2 plus 2d1, that type of thing. Let's do our delta y, or not our delta y, I was thinking of slope. Let's do our dy, our derivative of y first. So it's 1 and 2 for our 1d2 plus 2d1, so delta y, or not delta y, derivative of y. So it's 1 is e to the theta, times d2. And let me write down what I'm doing so you can follow along. I'm doing 1 d2 plus 2 d1. And maybe I can color code this a little bit. Oh, when I hit escape, it moved my camera or my screen a little bit. I'll say that's in yellow, that's in green. You can follow along a little bit better. So 1 is e to the theta. So e to the theta. D2, the derivative of sine is cosine. So times cosine of theta. Okay, good. Now I'm going to do plus. What is 2? 2 is sine of theta. So sine of theta. And then that's going to be multiplied by the derivative of 1, so times the derivative of e house. The derivative of e house, as we all know, is e house. All right. A bit of work for that numerator, but there it is. And now let's do the denominator. Again, it's going to be product rule. So 1 d2. So here's your 1. It's e to the theta. And then d2, the derivative of cosine is negative sine. So times, I'll put in parentheses here, negative sine of theta. And you might be noticing that sometimes I forget to do the parentheses, and that's okay. But if I want to be formal about it, I should really be adding those. I don't even know if it's formal. It's just kind of good practice, so you don't actually make a mistake if you think a square is accidentally on the outside. Anyway, 2 is cosine of theta. So I have cosine of theta. And then that's going to be times the derivative of 1, which again is e to the theta. And these look very, very similar. I wonder if there's anything that we can do. Oh, and then we have to immediately plug in pi over 2. I think, unless there's something that I can do, I guess the only thing that I'm seeing that I can do, oh, I definitely want to do this because this will save me a ton of work, is I can factor out an e to the theta on the top. So notice that this term right here has an e to the theta, this term has an e to the theta, this term has an e to the theta, and this term has e to the theta, which means I can factor out that e to the theta. So coming down to the next line, on the numerator I really have e to the theta being factored out, and what's left over, I have a cosine of theta plus a sine of theta. In the denominator, I'm also factoring out an e to the theta, and what's left over is, I'm going to rewrite these first cosine and then sine because it just feels better to have a negative sign in between instead of right at the beginning. So I'm going to say cosine of theta minus sine of theta. All right, and as we love to do, if anything is being multiplied and is on the top and the bottom, we're going to cancel that guy out. So now this is my function, and I'm going to plug in pi over 2. If you forgot where pi over 2 is, it's pointing straight up here. I'm going to leave that there because it's going to help us. So cosine of that pi over 2. Cosine is the x-coordinate. How far have I moved left and right? None, because I'm straight up. So cosine of theta, or cosine of pi over 2 rather, is 0. And I should probably show my work a little bit better. So I'm going to say cosine of pi over 2, and I'll go ahead and cross him out. That's gone. That's 0. And then I'm going to add sine of pi over 2. And what is sine of pi over 2? Well, pi over 2 again is at this spot, and sine is asking me about the y-coordinate. So how far have I moved in the y direction? Well, I've moved 1. So sine of pi over 2 is 1. So I'm going to say this thing is 1. All right, all of this is being divided by basically the same thing on the bottom. I have cosine of pi over 2, but now minus sine of pi over 2. And both of those are going to cancel out the same way, so this is going to be 0, and that's going to be 1. So our new equation reads, what is 0 plus 1 over 0 minus 1? And the answer is negative 1. I kind of want to do that in red. I like my red to be my final answers if possible. And there is our answer, and notice that we didn't have to make any substitution for x or anything. Like, no matter what we plug in, which is kind of cool, right? We're always going to have a slope of negative 1. Why? Why is that happening? I'm guessing it has something to do with e. E has really special magic properties that makes that negative 1. So I'm really impressed with the homework. We were able to find all of them in terms of x, and this one didn't have anything, so I'm still considering it a win. Everything was in terms of x except for number 3. I wonder if that actually can be solved. I'll have to think about that. I'll probably think about it more next year because I'm kind of done with lesson 2-4 now. There is the worksheet. Thanks for watching.